Hello everyone. Today is day 27 of us solving 30 problems in 30 days. 30 machine learning problems in 30 days. So let's go to our the list of the problems. Here is the list of the problems. And the day 27 problem is that we have to do image classification with a small CNN for CIFAR-10 data set. I think this is from deep learning. Uh, as you all know that in week 4 we are trying to touch deep learning and advanced models. This is the second problem in deep learning. uh, One update that I plan to do a 30-day similar challenge on deep learning, like 30 days of deep learning or 30 days, 30 deep learning problems challenge after this challenge. But I'll take some gap and read some fundamentals like from Kaggle and then start that challenge. I'm thinking of starting this challenge on 1st of November. So, yes, so this is our for second challenge on deep learning. Coming back to our this challenge. So let's see what this is about. So this is about building a convolutional neural network using CIFAR-10, a major milestone in deep learning for image data. I believe we'll have to do some classifications of image, like is it a cat or dog. I'll see if that is right, what I've predicted. So yes, let's get started. So again, the flow is going to be I'll go and use ChatGPT to help me through the problem. If I'll get stuck with any terminology, with anything new, I'll go and ask. So yes, this is how the flow is going to be. Uh, so yes, I'll say I'll move this to here. Hey, it is the 27 and here is the problem. So it says grade day 27 focuses on building an image classification model using a small convolutional neural network, which is CNN, on the CIFAR-10 dataset. The CIFAR-10 dataset is a popular dataset used for image classification tasks. Consists of 60,000 30 by 32 by 32 color images in 10 different classes such as airplanes, cars, birds, cats, and more. So the classes are going to be these. We'll have 60,000 images of size 32 by 32 color images. So yes, we'll have to do classification, I guess. We will build a CNN, convolutional neural network, to classify images from CIFAR-10 dataset into one of the 10 categories. CNN are well suited for image classification tasks because they can capture spatial. Okay, CNNs are well suited for image classification tasks. That's one thing that we have learned today. And why? Because they can capture spatial hierarchies and patterns like edges, shape, texture in images. Okay. So the data set is going to be CIFAR data set. Let me go and grab this data set from the internet. So here the classes are this: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. It has 50,000 training images. This sorry, it has uh, 60,000 training images of this size and 10 classes. I'll go and download it. No, not this simple submission. CIFR-10 Python version. Yes, we will download it from here. Let's see. It is a little big, so it is going to take some time. We'll come back to this one and read a little. It consists of 60,000 32 by 32 color images and 10 classes with 6,000 images per class. Okay. Hmm. The data set is already split into 50,000 training and 10,000 test images. Okay. So the plan for today's problem is going to be load the and pre-process the CIFAR-10 dataset. Build a CNN architecture with few convolutional layers. From yesterday's problem, we saw that deep learning algorithms or models work in layers. Like yesterday, RNN, LSTM model was working in layers. So then we will compile and train the model and evaluate the model on the test data and visualize the result. Okay, we will use TensorFlow and Keras like yesterday. So I'll go and dig more into the code later. But first, let me go and do what? Uh, okay, train the model, visualize. Yes, let me go here. We can see the data set like this: data batch 1, data batch 2. Here, oh, actually, we do not need to load the data, download the data at all. I'm sorry, I took some time. We can do so. We can simply go and download, get the data set from TensorFlow dot keras dot datasets. So let's straight away start the problem, as in the code. You do not have to download anything. I'll go create a file called day27.py, add it, and the problem is this, and the data set is okay. So let's do what? Import required libraries, which is TensorFlow as TF, then import TensorFlow.keras.datasets, import, not import, from, import CIFAR-10 with 10 classes from TensorFlow.keras.utils, import. I don't know why we are doing it, but let's import it. And do what? Can you please explain each line of code of step 1? Yes, so it is taking time. Let's wait for it to. Yes, I guess it has generated. Yes, let's go back and understand the code each line. Yes, yes, let's start. So let's go through step number 1 line by line to ensure each part is clear. This step is crucial for preparing the data for training and the CNN model. Here's the code. The first code is importing the libraries. This is the dataset. We are importing this library to categorical function from Keras, which will help us convert the class labels, which is in integer form, into one hot encoded format. And we know what one hot encoding is. So it creates separate classes for each. categorical data, each categorical class. Yes, so it creates, I'm repeating again, it creates separate columns for each categorical data. For example, I have a feature with two values, two types of values, gender with two types of values, male and female. So what one hot encoding will do, it will create two columns, gender underscore male, gender underscore female, and the rows where male was selected, one integer value will be set to that row and zero integer value will be set to that row for gender underscore female. If for a row where female was selected as gender, the two columns gender underscore male will have value 0 and the column gender underscore female will have the value 1. So this is how one hot encoding works, and we have used it and understood it in depth in our previous problems. So I would recommend you guys to go and follow those problems. uh, so yes uh, so yes so this two categorical is going to use one hot encoding format to convert the class labels. So yes, and now we are loading this data from CIFAR-10 dot load function, and loading it is, since we read it that it is already split into training and validation data. 50,000 for training and 10,000 for validation, that is testing. So we will simply go and import it. So what we are going to do, we'll go what? Step 1, load the data. We'll have x train by train, then we'll have x validation, y validation, and what we are going to do, we are going to do what, give one more space and load this data from CIFAR dot load data. So this is done. If I want to see the data, can I see the data? Let me go print it, run and run this day 27. Okay, so it is downloading the data first. Let it download the data. Going to take 10 seconds to download the data. Let's come here and then maybe we can understand this. Then we will have to do normalization. Normalize the pixel values to be between 0 and 1. We will need to see what the pixel values are from. So it says that this is an important step to help the neural network learn more efficiently. The pixel values in the image are originally in the form 0 to 255. Okay. Since images are represented by 8-bit unsigned integer, by dividing by a 255.0, we scale these values from 0 to 1. Okay, understood. 0 to 1. Convert the data, so we are scaling it. We have done this yesterday, we have done this in our previous problems also, because yeah, uh, keeping the scale low helps in training. So convert the data type of the images to float 32. This is necessary because the original pixel values are integers, but the neural network expects floating point numbers for better precision. Okay, so the neural network expects the numbers in floating points for better precision, so we are converting them into floating, and then we want them in the range of 0 to 1, so we are dividing by the max number, which is 255. Why do we need it? Neural network, especially CNNs, performs better when the input data is on a small consistent scale. Exactly, that's what I've said. This makes it easier for optimization, for the optimization algorithm to, to converge during training. If the pixel values are not normalized, the training process can be slower or less effective because large input values can cause instability in the learning. So yeah, large input values, so it becomes difficult to find patterns, right? So yes, that is why we do normalization, because it becomes easier for the optimization algorithms like Adam to converge during the training. So we normalize it. First, we convert it into 0 to 1 scale. Then we apply hot encoding. I have already told you why, using two categorical. Here we specify 10 because convert the training labels. That is why from integer to one hot encoding. We want to convert the labels. That here we want to specify how many labels, 10, and check the shape of the data. So this is the step number one. So let's go. It has downloaded the data. So this is how our data looks like. Here do you see the rows are looking like, the image is looking like this 239, 235. So we need to convert it into 0 to 1. So we have loaded the data. Then we need to do what? We need to do what? Normalize the image data. Normalize the image data. Okay. So we will do what? We will first scale the data to 0 to 1 range. So we'll do what? X train is going to be float, sorry, X train dot, what is this function? Converts the data type of the image to float. Okay, convert the data type of this image to float. What is this AS type? This is a pandas form called as uh, cast a pandas object to a specific data type. Okay, cast a pandas object to a statistic specific data type, and it is going to be float 32 and divided by 0. Then now my x value is going to be x validation dot convert the data type to float 32, and then scale it to between from I mean scale the values between 0 to 1. Then we'll do apply one hot encoding hot encoding. We'll apply two labels using what? Y train is going to be two categorical Y train. And how many labels you want? 10. We want to convert the 10 labels. Then we will do what? Just give me a second. Yes, minimize the terminal window and do what? Y validation is going to be two categorical. Y validation. How many labels you want to convert? I mean, to numeric. The labels need to numeric 10. And we will do what? Check the shape of the data. Check the shape of the data. Print xtrain dot shape, uh, x validation dot shape, print y train dot shape, y validation dot shape. And did I print something else also in the start? No, I have not. So I will go clear the terminal, run this file again, and we have 50,000 images of 32 32 size. It has uh, three sub arrays. It has three sub arrays. It has like 50,000 rows and 10 columns, 50,000 rows and 10 columns. So, yes, this is how it looks. Okay, now we are pretty much done with our step number one to load the data. Step number two is to build a small CNN architecture. Step number two is build a small CNN architecture. So this is going to be a little tough because we do not have that much understanding of deep learning concepts. But I do understand why we are doing it because something similar we did yesterday. So yes, let's start. We have to import two packages called sequential. Yes, and we have to import other packages that I'm not aware of. So let's go and import and then explore one by one. So I'll say thanks. Now please explain step two. First, we are initializing the model. So let's do what? Import the. Why? Meanwhile, it is generating the response. We can import the libraries. So from TensorFlow to Keras to models, import sequential. From TensorFlow to Keras to layers, import con2d, max pool 2d, max pooling 2d, flatten dense dropout. Yes. So first we'll do what? Initialize the sequential model. So we have to create a sequence of layers, right? Yesterday also we did something like that. So we have to build the network layers by layers in a linear stack in sequence. So this is a sequential model. Each layer has exactly one input and one output. The layers are added one by one and the data flows sequentially through each layer from input to output. So I'll go what do sequential model. I'll go simply and search it. So we have no ideas. So let me do not search anything here and understand that it builds multiple layers where each layer has one input and one output. The previous layer is helps the to build the input for the next layer, and the next layer helps builds the input for the next layer. So we are going to build this sequential model. So it is going to model sequential. You might be hearing some a little background noise. It is because my window is open. I had to open it because of my cat. Now let me go and close it. Yes, thank you. So I have created the instance of the model, sequential model. Now find convolutional layer. So yesterday we added the I don't know, LSTM layer. Here today we are adding a convolutional layer. So this is 2D convolutional layer that learns filter or kernels that capture special features in the images. So this will help us, I guess, with classifying the images. Oh, this is the convolution layer, I guess. Makes sense. 2D convolution layer. This layer, this layer, this layer. Okay, okay. 32. The number of filters applied to the input. Each filter learns to detect different features like edge. So we are applying 32 features. 3 by 3. It is the size of the filter. I guess this is the filter that we are saying. Can you see this submatrix with border red? So this is the size of the filter. 3 by 3 filter means that each filter will slide over the image and examine 3 by 3 pixel regions at the time. Smaller filters are common in scene because they allow the model to learn fine grained features. Okay, makes sense. So what it is going to do, we are defining the convolution layer. It is going to be 32 features, and the size of each filter is going to be this 33 by 3 matrix. Uh, the activation function is ReLU, rectified linear unit. The activation function applied after each convolutional is ReLU is widely, and this is widely used in CNN because it introduces non-linearity, allowing the model to learn complex patterns. So what it does, it converts the negative values to zero and leaves the positive ones unchanged. Okay, makes sense. Then we will do input size is of what size? 32, 32, 3. The image is of 32 by 32 pixel and has three colors RGB. So that is the size of the input. So this input shape defines the shape of the input data. Here each image is in the CIFAR-10 dataset has dimensions 32 by 32 pixel and three color image channels. So the input shape is 3 by 32 by 30, 32, 32, 3. The only input shape only needs to be specified for the first layer. The following layers will infer the shape from the previous. Yes, that's what I've talked about, right? The next layer will evaluate the shape of input from the previous layer. So we do not have this explicitly tell. So let's add the convolutional layer. Add first is it convolution? Convolution. Convolutional illusional layer. We'll do what? Model dot add see convolution layer which is of 2D type. Here it is, if we save it, it will have 32 filters of size 3 by 3, and then we are going to have activation function renew, and the input shape is going to be 32 by 32, and there will be three colors. Done. Then max pooling layer. So max pooling layer, this is a max pooling layer with 2 by 2 window. Okay, max pooling reduces the special dimensions height and width of the feature maps, which helps reduce the computational load and character of overfitting. Okay. How does max pooling work? It slides a 2 by 2 window over the feature map and selects the maximum value in each region, thus reducing the size of the feature map by half in both the height. Why we are using it? Pooling reduces the number of parameters, helps the generalize. Okay, so we are doing some sort of pooling so that by doing calculating the max from each region, and why we are doing it? Because it it reduces the number of parameters. I still do not understand much of it, but I'll go and use it. I am more concerned about understanding the intent. I'll not go and copy it, but yeah, uh, let's go with the flow and see how it produces and not get overwhelmed like I used to. So max pooling 2D that we have imported, and here we are using maximum pooling to get the maximum from each region. The size of the region is 2 by 2, and we do that to reduce the parameters, use the number of parameters. Okay, and then we are doing what? Second convolutional layer. The second convolution. So we have understood how what we are doing. The second convolutional layer will have 64 features, filters, and the size of the that region is going to be filter size is 3 by 3. Activation layer is this. As we have learned that we do not need to specify the input shape, so we are not specifying input shape. Another max pooling that we want to reduce the special dimensions of the map feature map, we will do same 2 by 2. Then we will add third layer. We will keep on increasing the size of the filters here also. So we have only three layers. Okay. So the twice of 122 is 255. Is it 255? And you do into 2 is 256. Yes. So yes, we do not. The third will be the one image. Right. So 1 2. Let's add second convolutional layer. So we'll do what? Model add convolutional layer. Here the filter is going to be of type 64. Size of the filter is 3 by 3. Activation function is relu, and we will add max pooling of size 2 by 2. Then we will add third convolutional layer. Model dot add convo 2D. Size of the filter is going to be 128, 64 into 2. The region, the filter size is going to be 3 into 3. And the activation function is going to be relu. And then we will apply again the max pooling. Size is going to be 2 by 2. Done. We now flatten the layer. We will do what? This layer flattens the 3D output from the convolution layer into 1D vector. This is necessary because the output of the convolution layer is still 3D, height, width, and number of filters. But the dense, fully connected layer expects 1D output. Fully connected layer expects 1D output, so we need to flatten the 3D output into 1D output. So we will do what? Flatten layer, which is we'll do what? Um, Model dot add what operation? Flatten that we have imported. Now we'll do what? Fully connected layer, dense layer. So we have one dense layer with 128 neurons that we have received. That's the last layer here. Each neuron is connected to every neuron in the previous layer. Yes, we saw it yesterday. The fully connected layers learn a non-linear combination of features extracted by the convolution layer. Okay, so let's build it. I still do not understand much, but let's build it. So I do understand that we have a dense layer where the each neuron, and it has how many neurons? 128 neurons are connected to the previous layer. So the activation function is YOLO, and then we will apply dropout. And dropout is a regulation technique used to prevent overfitting. So it will randomly drop out 50% of the neurons in the layer. This forces the model to learn more robust features and prevent it from relying too much on the specific neurons. Okay, so we need to regularize the overfitting. So that's where we are doing dropout. So model dot add dropout. Dropout, how many percentage you want to drop out? 50%. Then output layer. The output layer will have, this is the output layer with 10 units because there are 10 classes. Each unit corresponds to one class. So how many layers you want in the output? 10 layers. So output layer. So we'll do what? Model dot add dense have 10 output because we have 10 classes. Activation function is reload. Then is softmax. We are using a different activation function. Why so? Let's see. The softmax activation function is used for multi-class classification problem, which is today's problem. It outputs a probability distribution over the 10 class where the predicted class is one with the highest probability. Okay. So we are outputting 10 layers for 10 classes. Now the output will be, as in it will predict it to be that class which will have the highest probability. So softmax activation function is going to do that. This ensures that the output sum to 1 and that represent the probability that the input image belongs to each class. Okay. Then we will print the summary of the model. This prints the summary of the model architecture showing each layer and the number of parameters in each layer and the output shape of after each layer. So it makes sure that the architecture is built as it is intended to. So let's print this summary. We'll do what? Model dot summary. Should I need to run it or see what is there in the step number 2? Because yesterday it took 7 minutes to train the model. Gladly we ran it in one go. So let's do what? Complete the rest of the model, which is simple. Compile the model, that the architecture we have built, split into, train the model, and then visualize the model. Nothing fancy. And then we will do what? We will make prediction. So let's do what? Let's compile the model. So for compilation, we are going to do what? Step number 3 is compile the model. So we will do what? Model dot compile. Optimizer is the function that we want to optimize, as in from, yeah, and the loss function, as in the function with which the loss will be calculated will be categorical cross entropy. I don't know what that function is, so we will leave that as it is. And the metrics to calculate the loss is going to be, and calculate the efficiency is going to be accuracy. I'll copy it again and done. So we have compiled the model. Now we are going to train the model for 10 to 20 epochs depending on your computational resources. We'll also include the so this step yesterday took like more than 7 minutes. So we will, on training the model, took more than 7 minutes. So yes, so we will compile and train everything all together. Train the model. We'll do what? We'll do history model dot fit. Here we specify we want to fit on training data, and this is going to be the target. Epochs. We know epochs is that how many iteration we want to perform, and each iteration the function will be this. metric will be calculated using accuracy, and Adam will be applied. This optimizer, that is Adam, will be applied to optimize the each that it corrects and learn from the mistakes from each layer, from each epoch, is Adam. And then that is number of iteration through entire data. And the batch size it will take, within each iteration it is going to cover entire data set in the batch size of 64. And the validation data that it is going, so while training it is also going to make sure that it is learning from the mistakes. So for that it is, and evaluating the accuracy and evaluating the loss function. For that we need to specify the validation data, right? So the validation data it is using X validation, Y validation, that is it. Once done, we will evaluate the model and visualize the result. Step number 5 is evaluate the model and visualize the results. So let's do what? Evaluate the model by doing what? Using evaluate function. So we'll do what? Validation loss, validate the accuracy. Validate the loss, validate the accuracy. And I'll do use the evaluate function of the model against the test validation, X validation and Y validation. Once done, print the accuracy. We are going to print validate accuracy is going to be validate accuracy. Yes. So once done, I don't think that we need this step. So this step is like, so yeah, we do need this step because this is, yeah, let's complete this step. We will print the step, the accuracy. Now we will plot the accuracy and loss. So we will do what? Input matplot.py plot as plt. Give one extra space. Visual visualize. So we'll visualize what? We'll plot a figure of size. What size it says? 10 is to 6, and we'll plot accuracy. Plot accuracy. It will say subplot 1 to 1, plot history dot history. I'll go what? I'll say please explain this. Can you please explain this from step 5? Okay, so it is generating. Let's wait. Okay, let's start. So it says we need to now plot it. This says we create a subplot where we can plot multiple graphs a side by side. This one to one means that the figure will have one row, two columns of subplots. Where we are currently plotting the first subplot. Okay. We will, when we will see, we will understand it, I guess, right? So let's do what? Let's build it. So this says that we are going to use the accuracy from the history that we have predicted, and then next we are going to get the we are going validation accuracy. So this okay, so this is going to be the actual accuracy, and this is going to be for the validation accuracy. Let's see if that is right. This plots the training accuracy for each epoch. The accuracy values are stored in the history dot accuracy list, which is recorded during the training. It shows how well the model is performed on the training data over the course of training. As the model learns, this value should increase. Okay. This validation accuracy shows how well the model is generalizing the unseen data, that is the validation data. If the validation accuracy improves along the training accuracy, it suggests that the model is not overfitting. Okay. Okay, so it shows how well the model is performing while for the unseen data, the validation data that we have kept, like the 10,000 images. If the validation accuracy stops improving or declining while training accuracy continues to improve, it could indicate overfitting. Okay, we will see that. Then we will see the training loss and the loss during the validation. The training loss is the measure of how well the model is doing in terms of its prediction. Lower the loss indicates that the model predictions are getting closer to the actual labels. Validation loss is how well it is performing on the unseen data. Again, the lesser the loss, the better the model is prediction is. So let's go and visualize it. Go back to the code. Yes. No. Here. So we are building a subplot, and we get the first we are doing what? Plotting accuracy. So here we are doing history. We get this value accuracy. We build that, and the label is training accuracy. Then we plot history validation accuracy for the validation data, and the label is validation data accuracy, and the x label is going to be epochs. The y label is going to be the accuracy, and then we will use legend to see which line represents what, otherwise you'll get confused. Then we will plot loss. I'll copy it, and here my graph is split into two, 1 by 2. This is the first section, and this is the second section. Here now we are plotting the loss, and the next is going to be validation loss, and it is training loss during training. It should be minimum, and it is loss for the validation data, that is the unseen data. It should also be minimum. Here again epochs, and this is loss. And once done, we will simply show it. uh, I will not go and run because the model takes like minutes, like 7-8 minutes to run. Earlier yesterday it took like that much amount of time. So I'll go and complete. So we have understood until now what it is should do. Should visualize the create a plot, or we should see a plot figure in split into two parts. One should show accuracy, other should show loss. Now we should do what? Step number 8, 6 is make prediction. So we are going to generate a sample image, and we are going to see what type of, whether it detects the image correctly or not. So what we are going to do first, we are going to import numpy as an np, and then we'll do what? Pick a random image from the test set. We'll do pick a random image from from the test set. So what we are going to do, we are going to create a random integer, random, I'll say random index, I'll say it is 50,000, right? I'll say 4, I'll say 334,467. Random image is going to be X validation. Oh, it has 10,000 only, no? We are getting that from the unseen data. We are not getting that from the trained data. Of course, it is going to predict nicely. So unseen data, it is going to be 5,464, 5. And this is going to be the index, random index. I could obviously use the random in to generate this. Then we will make the prediction, make prediction using the trained model. We'll do what? Model predict. So prediction model dot predict. First, we'll create an image using numpy dot expand dimensions, random image, and columns, and then predict. We have to predict the class. So we are going to use this. I don't know why we are doing this. Can you please explain this in step? I'll simply say step 6. Generates the random image. Pick a random image from the test set. Make prediction. Here we are doing what? This adds an extra dimension to the image array so that it matches the expected input shape of the model. The input shape of the model was 32, 32, 3, so it is doing that. Ba- 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 ba. Now to predict the class, we extract the index of the highest value. That is the probable. Okay, so predict the highest value. So we get the highest value from this argmax from the prediction, and that is going to be the class. We get the index of that, the index of the maximum value in the error. So it gets the max index of the maximum. So prediction has the let's go and print this prediction also. Prediction class. So numpy dot get max value from this array prediction, and along the row we want it. I am really curious to see this prediction actual class predict, say prediction array. So it will have prediction, and we'll see the actual class. Print actual class of the random image is numpy dot again get the maximum value from this array of y validation, random index, and once done, We will print, it will print that, and then print the predicted class. Predicted class. Prediction class. We saw that it generates the probability from for each class, like from where it can belong to, and then it picks the maximum probability, and based on that it predicts what type of the image is, image belongs to, what class of the, what type of the class the image belongs to. Now we will simply show the image, visualize the image with the prediction. So it uses matplot library to display the randomly selected image using image show function. Uh, yeah, and this adds the title of the plot showing the predicted class. Title this will display the predicted tree, indicating that the model predicted class of the tree. Okay, plot. I image show. We need to show which image? Random image. Okay, we want to select it from Y. Yeah, and we will get this the title of the predicted class. So we need to show the title of the predicted class. Predicted what? It has predicted this. It will show the class name and simply will show it. We'll go, and I quickly want to go back and see this was correct or not. Yes, validation only, but yes. So I'm going to run this program because it looks solid. We have understood everything. We see some warning. Now we see it doing what? We see everything, all the layers here. Now it is, we see the output of each epoch. So we have specified 10 iterations, epochs. So let's wait for some time. Each epoch is taking 13 seconds. So I guess, yeah, 13 into 10, 130, so 2 minutes. More than 2 minutes, around 2 minutes it is going to take. So we are on the third epoch and we do have an error on line number 83, 83, 83, 83, and we do have this error. sad. So we might have to run again. I recommend you guys to go and forward it to two next 2 minutes. Okay, we are on the sixth epoch. Mm, two more left. Okay, we are on the final. So this is how it is working. It is constantly increasing. This is constantly decreasing. Let me take the screenshot. We saw that the loss should be minimum and the training should constantly increase, but the second is exactly opposite. So I do not know what to figure out from that, and I'm not able to now see this line number 95 is creating a problem here. It says you know what I have to do? I'll go and select the random index of x, and here we need to do x validation, right? Label, right? One more time I'll run it and say, hey, so the model ran, and here is how it is the evaluation visualization lot. Uh, how do you think the model has performed? I'll go paste the model from my screenshot and what uh, ask ChatGPT. Okay, so it is steadily increasing. So it shows that the epochs which shows that the model is learning from the data and improving its ability to classify the training images correctly. By the end of the ninth epoch, the training accuracy reaches the approximation of 0.75%. Complete, yes. So accurately, how accurately it is, the accuracy is constantly increasing. Here it should decrease. So here it is performing really well for our training data. For validation, the orange line, the loss is okay, okay. Sorry, the loss should be minimum, right? So it should constantly decrease. So that's what is happening. So I think the model is performing really good. So here the orange, this is for the validation data. This is lower here. The validation accuracy starts lower than the training accuracy as expected, but follows a similar upward trend. By the ninth epoch, the validation accuracy reaches the 0.97%. Importantly, the validation accuracy is close to the training accuracy, which shows a positive sign that the model is generalizing well to unseen data. So it is accurately doing for the accuracy and the what validation data or accuracy data. The logs should be minimum that we can see here also. If I do what? The training loss steadily decreases the epoch's progress. This is good indication that the model is minimizing the error. Correct. For the validation also we see a decrease. It means that the model is performing really good. The model is showing a healthy learning curve both for accuracy and loss for the training and validation data, which means the model is performing really good, showing no signs of overfitting. So I'll go what? Uh, and this is the image that it has printed. I don't know what type of image. So I'll go take screenshot and let's go back to this. The random image class is 4. This is the predicted values. The maximum value is coming 4.3, 5.4. This is 9.13, 8 points. So this is the maximum values 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the epoch. Okay, and the prediction array is this. The maximum of the random index, the maximum actual class of the random image is 4, and the predicted class is okay. We did not run the predicted class, should be this, the predicted class, not this. After showing, it did not show predicted this. So I'll go back to this visualization step. I'll go and run it again, and I should be able to see how the model is performing by going to this predicted class here. It has predicted 2. Okay. So it predicted 2, but the actual was prediction 3. So for a random image, it did not predict correctly. It predicted 2, but actually it was 4. So I guess for random it did not predict nicely. Uh, Potential reason we are running it one more time. I guess I'll wait like 1 minute more to see if it will predict this time correctly, because we are doing selecting the image randomly. So let's wait for 2 more minutes. It should be done, and we should be able to see if it predicts one more time correctly, if it predicts correctly for the random image. So let's wait. We are on the seventh epoch already. Okay, we have already understood this graph. This is the image, it predicted 3 and the actual class was 1. So yes, I'll take the screenshot. uh, so it did not predict nicely. So yes, this is how the model is performing. It looks really solid for like starting problem to of deep learning. We have understood a lot of new topics today. We explored how to add densing, how to handle the images, make sense out of it. So it was really good. Let me go and commit it. And I'm now really looking forward to complete this challenge and move to the next challenge, which is about deep learning. So yes, now I'll go and commit it. Add code for day 27. Push it to the main repository. Let's see if we can see the push change. So yes, the change is here. So yes, let's close it, and in the evening you can find the detailed textual representation over the tech journal and the video of it that I'm recording right now, the development log on the YouTube channel. So thank you very much.